I have with me Surya Nimagada. He is the distinguished engineer working on the VMX product. We have Paul Abbott, who's going to be our solutions architect, doing the demo for us. So I'm the product manager for the Virtual MX. So what we're going to do is give you an overview of the product, the use cases that we're actually targeting, and then we're going to head into the demo.
Sorry to do this to you, but since your mic was not on when you introduced yourself,
okay.
Could you just do the introduction again so that we can have it on the video nice and clean?
Sorry. Okay. Hi, my name is Arful Haq. I'm the product line manager for the Virtual MX product. I have with me Surya Nimagada, who is the distinguished engineer for this product, and Paul Abbott, who's the solutions architect. All right. So, not sure how many of you are actually familiar with the MX products. I'm going to do a quick introduction of what we actually do on the MX product. So, the MX is really a Swiss Army knife of the routing product portfolio. We have everything starting from 80 gigs all the way up to terabits of capacity. We use one architecture. We have a single silicon architecture that we actually use across all these products, and we have use cases across enterprise all the way up to metro, service provider edge, and data center as well. What we've done with Virtual MX is taken this product, all the software around it, and virtualized it. And I'm going to talk about how we did that and how we're going to maintain feature parity and really make this a product that you can do everything that you can do on a physical MX product, you can do on a Virtual MX. So that's going to be the concentration of this presentation. The MX has wide deployment right now. It's deployed in a lot of the large web providers and in internet service providers as well. So the use cases or market segments that we're actually playing in, as I was mentioning before, the MX plays a role in the enterprise edge, in the aggregation, in the service provider edge, as well as in the data center. So for VMX, we have cross-market applications such as the virtual route reflector. That's actually a really easy use case for us because it's mostly control plane heavy, and the fact that we have virtualized Junos makes it very easy. So it's going to be able to offer very rich functionality, as well as you can use the compute resources available on any type of server to actually host this functionality. Right, so you're no longer limited by a routing engine on a router. What your limit is, what is the capability of that server? And then we have use cases as a CPE, as an enterprise WAN router, virtual PE. We have use cases in the BNG broadband gateway market, as well as in the data center / cloud market segment. So I'm going to talk about specifically these use cases over the next few slides after I do the brief product introduction. And one of the most interesting things about this product is the fact that the way we've gone about developing it. So anytime we actually develop a feature on a physical MX product, we actually get that feature automatically on the Virtual MX. We don't have two different R&D efforts for this product. We're not developing a virtualized forwarding plane separately from our physical forwarding plane. So every time, for instance, we talked about EVPN, VXLAN today. So EVPN is developed on the physical MX product. The control plane is available in Junos. You automatically get that feature on the Virtual MX product. So that's one of the big things that we concentrate on. Not just building a virtualized product, but making sure that it's feature parity with our existing product portfolio. So to go into the product, there's two components to the product. There's the virtual control plane, which is shown here as a VCP. Essentially, it is Junos running in a VM. And then we have the VFP, virtual forwarding plane, which is actually native Linux. So this is our software forwarding plane. This is where we host our software forwarding plane. So the control plane, as I mentioned before, it's Junos, so it just maintains Junos cycles. So every time there's a Junos release, you get an image for the virtual control plane. The virtual forwarding plane is our what we call Trio software forwarding plane. Trio is the name of our ASIC architecture on our physical MX products, where what we've done is virtualized that architecture. And we make use of Intel DPDK here. So we make use of Intel DPDK libraries to do things like pull mode. So we constantly pull the NICs to essentially move packets from the NIC into the user space. We do a lot of other things actually, and if you have questions, Surya is here. He can definitely help answer a lot of those questions. We make use of SRIV. which is a PCI pass-through technology, right? So this allows you to move packets directly from the NIC into the guest space without having to do a memory copy on the hypervisor side. And then we also have VirtIO technology available. So if you want sort of power virtualization technologies where you're not bound by the NIC, where you have a direct mapping between the guest VM and the NIC, you'd rather have the ability to move the VM around, then you can actually use power virtualized technologies as well. So we support both of those. This VM for the virtual forwarding plane can be hosted as a VM, or it can actually be a bare metal. So it's up to you. It's your choice. And from an orchestration perspective, we have this working with OpenStack Kilo. So we decided to go with the Kilo release because it offers a lot of the NFV functionality that we require. For instance, if you keep in touch with Kilo, we have essentially things like NUMA pinning, and also things like huge page memory support. Those are some things that you actually require in an NFV like this. So that's why we decided to go with Kilo. We have heat templates that you can use to bring up the VFP and VCP instance. There's a Linux bridge. Because these are two separate VMs, you do actually need to configure a Linux bridge to ensure you have connectivity between these two VMs. All it is a layer 2 bridge. There's no IP addressing on that bridge. You're communicating between, if you, for instance, transit packets going from your forwarding plane to your control plane, those are using that Linux bridge.
So is this utilizing an existing like DVS switch, or are you just literally creating like a tunnel, a layer 2 tunnel? No. Well, no, you'd still have to use the virtual switch.
It can be any method that Linux provides. Like we can have Linux bridges, which is as simple.
Right.
And you can have Open vSwitch if you want high performance.
But they don't need like an uplink. I can create like a dumb.
You can create it.
No uplinks and just use it just for secure communication between.
It's just a soft bridge.
Right.
So you're doing ML2 on the Neutron side?
We don't use ML2 here.
Yeah, we don't need it particularly. Yeah.
You mentioned you support Open vSwitch, so I was curious about.
No, yeah, we just take whatever Open vSwitch is comes to talk.
So that means the two VMs have to reside on the same host, right?
Not necessarily. You can actually have these two VMs reside in separate hosts if you want that type of architecture. All of our testing so far is actually on a single server, but yes, the architecture allows it.
You can have an overlay to connect these across two servers.
But obviously, you would want this on more than one host in your environment, as well as distribute it out. Like
Good
the
question.
VFP, you would definitely want to have more than one VFP and.
Yeah, so it's actually one of the reasons we went with this architecture is the fact that it allows the scalability where you can have multiple VFP instances and a single control plane instance, right? So we're starting with that architecture, so we're actually going through some internal programs to actually look at that, so how we can actually scale this out.
But so you said you create a tunnel in the case where the VFP and the VCP are on two separate hosts? Or if you have two VFPs, same kind of concept, right?
You don't need a tunnel, actually. All you need is layer 2 connectivity. So if you're using, for instance, a VLAN to communicate between those two servers, as long as we have layer 2 connectivity between the VFP and VCP instance, we're okay.
And if you don't, like if I'm all layer 3?
We can have a tunnel kind of, an overlay kind of.
Okay. That's kind of why I was asking the ML2 question, because if you have to orchestrate overlays between these hosts, you need some sort of OVS orchestration in addition to the orchestration needed by setting these VMs up. You need both.
Okay.
So,
as you said, like in the first product, we have everything on the same server.
Oh yeah.
We can use the.
It's a lot easier on the same server.
Yeah, it is.
Yeah, it gets a little bit tricky. So I have one more stupid question. Why is one FreeBSD and why is one Linux?
Good question.
You knew that was coming.
Yeah. So Junos is based on FreeBSD. Junos is we don't have Junos on native Linux right now.
Okay.
That's why.
Okay.
Yeah.
But today it's one-to-one relationship, right? You could, for every VFP, you need one. You can type one VCP to only to one VFP, right?
That's the way it is right now. Actually, in a couple of months, we'll have VCP redundancy. So you can actually do, like, for instance, in a router, you have dual REs. You could do those types of things as well. You could do two VCP instances mapped to a single VFP instance.
Okay.
This is what is available today.
So as I mentioned, orchestration-wise, you can use OpenStack. We actually have prepackaged scripts that come together with the package that you download, and Paul's going to walk through those scripts that all you have to do is modify a configuration file, and launch the script. So he's going to walk you through that, so I'm not going to steal his thunder. All right, so let me talk about the software forwarding plane and sort of how packets are processed on the virtual MX. So there's three components. There's a receive thread, there's a transmit thread, and then what we call a worker. So worker is pretty much doing all your packet processing. It's doing the lookup. So for instance, we send the first 128 bytes of a packet to the worker to do the lookups, to do any sort of policing or any sort of routing functionality that you would do in an ASIC. What the receive and transmit are doing is receive and transmit is where a lot of the DPDK plays a role. So we actually have pull mode drivers that are constantly reading packets from the NIC into the receive thread. We do things like pre-classification. So for instance, control plane packets are always pre-classified versus transit packets. So even if you have a congestion scenario on your ingress, we always maintain BGP session, OEM sessions, right? So we want to make sure that there is no, you're not dropping your control plane packets. We do things like flow hashing. So we map a flow into multiple cores, right? So we can load balance the packet processing across multiple worker threads. So the worker threads are primarily doing the lookup functionality. And on the transmit side, we do things like QoS. So we actually have a model where we have 6 queues per VLAN, and we've tested this up to 4,000 VLANs on the transmit side. Right? So, and within those 6 queues, you can do prioritization. So for instance, you can prioritize voice traffic before video. So we have a high queue that is a low latency queue. We have a medium where you can put in video, and then we have 4 low priority queues that we use a weighted round robin scheduler.
All right, a question.
Yeah, go ahead.
So typically I would use like NIOC, right, to do network I/O control.
Okay.
In my vSphere. I need to disregard that and go straight to this to start doing like bandwidth throttling and QoS and things like that? Or do they work together?
Firstly, this is KVM supported VMX at this point, and the NICs are directly controlled over or the SRIOV, which is like you have direct channel pass through. Right. You don't go through the hypervisor. So it directly goes over your NIC.
Right.
So that way VMX completely does the quality of.
So SROV is required?
So no, that's one of the options. So
okay,
we do
I thought,
VirtIO as well.
I thought it said that it was
so I think
capable.
Yeah.
That's what I saw.
The way I would look at this is we schedule packets towards the NIC, right?
Right.
So how the packet gets from the NIC out is, if there's some other mechanism that you're using, then yeah.
Well, I can see that being a huge issue, right? Because if I'm doing, it's not an issue on your part, it's an issue on my part.
Okay.
Whereas if I was to get in and, maybe I'm overthinking this, but if I was to put some sort of QoS or any kind of throttling in your product, but also on a vSphere, traditional network IOC, network IO control type things, I'm doing double.
Yeah.
I see.
Right, and yeah, so then if I get into an issue, number one, I have to remember, hey, I did this here and did that there, and
Yes.
it would be cool if it could work together. Obviously.
Yeah, I mean, I'm not very familiar with the network IOC. We'll definitely get on top of that.
Okay.
Yeah,
Cool.
we actually we just started. We finished qualification for ESXi 5.5. So we actually have an image that works with ESXi 5.5. It'll be up on our website very soon here.
Okay.
So yeah, we have ESXi 5.5 support with SRVN VMX Net 3.
Okay.
So there's a punt path as well. So for instance, any control plane packets go up to the host interface towards your control plane VM. All right, so performance. What we're showing you here is a server where we ran this test. So it's an Intel Ivy Bridge server, 4 cores for the forwarding plane, 2 cores for the 1 core for the control plane, and 1 core for the hypervisor. We use 12 gigs of memory. You don't need 12 gigs of memory. The minimum amount of memory we support today is around 7 gigs. You give 6 gigs to your forwarding plane and 1 gig to the control plane. We've qualified all of this on Ubuntu, so we recommend you use Ubuntu 14.04 and the Linux kernel 3.13. And the NICs that we're using for this test are the Intel 82599 NICs, because those are the NICs that support sRIV technology, right? Now, Intel has other NICs. For instance, they have an XL520, I believe, that also supports sRIV. As long as the NIC supports sRIV, that's where you get the better performance. If you want to use VirtIO, that's fine. You don't actually need these NICs, right? And Paul's actually going to cover a lot of this detail in his presentation as well. So with 4 cores for forwarding plane, we were able to achieve 20 gigs bidirectional traffic, right? So if you had 2 ports of 10 gig, you would see traffic going in one direction through one 10 gig node and then coming back out as well. So it's really 2 10 gig ports of traffic at 256 bytes, right? And we can achieve that at 200, with iMix, we can probably achieve that 20 gigs bidirectional, for iMix, no problems. So this is one test we did. And we're actually going to show you this test as part of the video. And this test includes a full forwarding plane of a PE router. So for instance, we had 500,000 routes in the forwarding plane. We had firewall filters. We had VPN instances. We had, I think, close to 600 IFLs. So it's a full configuration, and we were able to scale this to 20 gigs with 4 cores on the forwarding plane. If we were to take that further, within a single socket, we can do about 40 gigs bidirectional with a total of 8 cores for forwarding plane. And again, full-featured functionality, right? So we're going to demo to you what we actually mean by full-featured. The fact that it has L2VPN instances, has a full internet routing table, firewall filters, and all those things. So with this type of sort of throughput, we can easily do 80 gigs on a single server if you have 2 instances. We map everything to a socket, so you have a single instance on a socket, and you can instantiate another VMX instance on another socket, and you can get about 20 gigs. Now, 80 gigs. Now, the reason why I show this per socket is because the memory and all the associated functionality characteristics of the cores are all associated to a socket, right? Now, if you span across sockets, you end up having issues because you're doing memory copies from another socket, right? Yeah, exactly. So this is called a NUMA boundary issue. So so all the testing is done within a socket.
So the 80 gigs is that's probably
2 instances.
SROVs required.
Yes, that's SROV. Yeah,
Right.
yeah.
You can't do that with VirtIO.
No, we've seen with VirtIO about 3 gigs of performance so far.
We need some support, some more. It also depends on how fast the hypervisor can hand over the packets to you.
Okay.
All right, so let me talk about the use cases, and then we're going to head into a small licensing section and go into the demo. So the first use case is the virtual PE here, where essentially a service provider is using VMX to provide a layer 3 VPN service, layer 2 VPN, layer 2 circuit, VPLS, what have you. Any sort of carrier-like services that you would offer to an end user, you can offer using this, the virtual MX. And the idea here is that large service providers have a lot of central offices, hub locations, and they're beginning to put compute resources in these locations. Some of them already have compute in these locations. So why not instantiate a VMX instance, a 20 gig VMX instance that's able to service that metro area and offer those types of services on that VMX instance. Most of these customers are low bandwidth customers. They're customers ranging from 1 meg to 10 megs. And it's also a very distributed deployment, right? So for instance, there are some customers that are looking at a dedicated PE per customer, where I'm providing administrative separation and the fact that I can deploy features for this particular customer as and when the customer needs, right? So there is some very interesting deployment scenarios that you can come up with, the fact that you have virtualized the PE functionality. So the value proposition from our end is the fact that we have all the features that we support on the physical MX. We also have some secure transport features like IPsec. So if you're, for instance, a service provider or a small provider that needs to go to a new geography, and you may not own that last mile, or you may need to come in through the internet or through a partner network, you want to secure your traffic. So we can actually support site-to-site IPsec tunnels and group VPN technology for IPsec VPNs. So the second use case is a data center gateway. So we talked a lot about a gateway router in the data center where you can terminate MPLS over GRE, VXLAN, EVPN technologies. Not all locations, I've talked to multiple small hosting providers where the traffic exiting the data center does not exceed 20 gigs. So this is actually a nice solution. You can instantiate VMX on a server, make it your gateway, right? So it's facing the internet or going towards an MPLS cloud if you're doing MPLS VPNs, but it's terminating all that SDN gateway functionality that Damien brought up today, right? So it's able to terminate VXLAN, MPLS over GRE. It can even be a gateway for the Contrail cloud. So the Contrail requires a gateway to communicate between the virtual and physical world, and that's one of the applications that VMX can play a role in. So this is one of the big advantages with the architecture we've chosen, the fact that we can be feature parity with all the capabilities of our physical products. Another use case is the enterprise WAN router, where we know large enterprises and some government institutions, they want to be able to set up their own networks. They buy an MPLS circuit from a provider and set up their own overlay network, right? So with this technology, you can do MPLS over GRE, VXLAN, or even Groove VPNs, right? So we're actually getting in Groove VPN functionality on the VMX. So you can set up your own overlay, do your own routing. All you're doing is buying a circuit from your MPLS provider. And the granularity of the VMX instance starts at 100 megs. So I'll talk about the licensing. So that's one of the cool things, that you can start at 100 megs, you can go all the way up to 40 gigs with the licensing architecture that we have. And the last use case is a virtual private cloud gateway. So this is essentially extending your enterprise up into the cloud. We know, for instance, we're working with Amazon on this actually right now. So Amazon has multiple regions. You instantiate a VPC instance across regions. There's no way to do routing between regions. Amazon doesn't offer routing between the regions. You have VPC instances. So you can instantiate VMX as a gateway router in a VPC instance. You can set up IPsec tunnels from your enterprise into that VPC instance. You can even do a Groove VPN across multiple VPC instances into your enterprise. So this is one of the applications we're looking at as well for VMX. So how does the licensing work? We have 3 different application packages we call Base, Advanced, and Premium, and I'll talk about what each one of those application packages actually entail. We have capacity-based licensing. It's per instance license, and you have 2 payment options. You can either do subscription, you can do a 1-year subscription for this product, or you can do a perpetual. So you buy the product and in perpetuity, right? And you can do the software upgrades, just pay your annual service fees. So the way the application packages are divvied up, so you have Base, which just provides very basic IP functionality. This is really just for, if you need small fib, basic IP functionality, some layer 2 functionality, this works really well. It's the lowest tier. Advanced gives you a full internet routing table plus more L2 functionality, things like VPLS, VXLAN, EVPN, IP multicast. And then the Premium gives you layer 3 VPN. And all these tiers are additive, right? So you buy Advanced, you get Base. You buy Premium, you get Base and Advanced. And the way the licenses are structured, anything below 1 gig, we include everything, right? So we include Base, Advanced, and Premium. You don't actually have to buy separate licenses for that. Anything beyond 1 gig, we have the tiers. We have Base, Advanced, and Premium, right? So, and if you want to try this out, we have it available to download. So you can go to our website, download the VMX. It comes with 30-day license, so essentially 1 megabits per second on the forwarding plane for 30 days, and you can play with it, right? Comes with full functionality. We don't cap the functionality, we just cap the number of routes that you can put in the fib and rib. We have about 32,000 routes you can put in the rib and fib. I think that's more than sufficient for a lot of testing purposes and functional testing. But yeah, anybody's willing to, you can download it and try it out.
Just curious, what happens after the 30 days? Would the feature stop working or the throughput drops?
We actually cap the throughput, so your forwarding plane goes to 0 megabits per second.
Oh, that's
Zero?
awesome.
Yeah. At that point,
Well, that's a huge, like,
at that point, we can give you a license, a trial license. We have 60, 90-day trial licenses that we can give you. Yeah. So we'd be happy to give anybody here a trial license to play around with this. Yeah.
What's the
That's
form
pretty funny,
factor? You said this
actually.
comes in multiple VMs.
Yeah.
How do you actually download it? What does it come as?
Oh, it's a package that Paul is going to talk about right now.
okay,
so he's
cool.
going to go through the actual installation and show you how everything is done.
Cool. And my second question, feel free to also say this is coming later. Awesome integration with Vagrant and whatnot using the VSRX. Any plans to do that here?
Yes. So we actually have Vagrant integration. We actually have. We'll publish that as well. Yes,
Sweet.
we do have that.
Cool. Perfect.
Yep.